It is a pleasure to host Professor Moti Friedman from the Faculty of Engineering at Bar-Ilan University, and he's going to tell us about synchronizing human networks. Moti, the floor is yours.
Good. Thank you very much. Okay. My main research field is actually quantum optics, and somehow I found myself in this field. It started, well, actually in my PhD, I studied many synchronization in phase of different systems, mainly lasers, fiber lasers, mechanical systems. And I always wanted to study somehow the synchronization of humans, how to synchronize humans. And I couldn't find a way to do it. And I was thinking about dancers, how do I make them couple to each other and all this, and I couldn't find a way. And actually, this research started when I joined a project by the Nano Center, by the Center of Nanotechnology in Bar-Ilan, where they started some kind of science museum. But it wasn't like a science museum like what you have in Haifa, where you see like a block fell, and you look up and you understand things in physics, but it was supposed to be more of an artistic museum where artists come and join some lab and understand what's going on, and then they create something from this interaction between the artist and the scientist. And I was joined with a musician, and I started talking with him about synchronization and stuff like that. And then he said, well, music is the solution. With music you can do it. And then when we started thinking about it, like everything just blew up. It was obvious what we need to do. And we started doing this piece for the museum. And while working on this piece for the museum, which was only supposed to be a demonstration of how synchronization happens in nature, we discovered new physics and new stuff. And this is what I'm going to tell you about it. And then we started like a new field of research. And this musician, which actually did his PhD on this work because he was a PhD student during the time, is now in the Technion, and he opened, Elad Schneiderman opened a lab dedicated to this research. So, yeah. Yeah. My first son. Okay. So let's talk about synchronization of human network. Well, synchronization is important, okay? And this is something that probably most of you have seen. If not, it's nice. You have these pendulums, and they are interacting through this wooden piece. And then you synchronize, because synchronization is whenever you have, for synchronization, you need some kind of energy transfer between the different elements in your system. And when you have this energy transfer, and the energy transfer is large enough compared to the tuning between your in this case pendulum, then you get synchronization. And this is correct in every system. And here are like nice birds that synchronize movement between them. How you say zalzelim in English? Starling. And think about it. To do these shapes, there is no like a mastermind that tells them, okay, this one, you will go this way, you will go this way. Everything here happens because of the interaction. All these shapes happen only because of the interaction, with no masterminds that control their movement. Okay. But let's talk about synchronization of humans. Because synchronization of other systems is well investigated, and we have like good analytical methods and good models to describe them. But in humans, sometimes things break down. And synchronization of humans is important to politics, it's important to the economic, religion, crowd flow in the army, big projects. You need synchronization, you need human synchronization in everything, and you need to know when things will work out and when things will break down. And in each one of these aspects, things can go well and things can go terribly wrong quite fast. Okay, so there are many research on this topic about synchronization of people clapping hands, synchronization. There are two things that this clapping hands. There are two that I really like about this. This one, which is the synchronization on the Millennium Bridge. People know about this research. There was this Millennium Bridge which opened in 2000 in London, and apparently they did it wrong. And when people start walking on it, it starts wobbling around. Just when you have like too many people, it starts going like this, and everybody started going the same way. So it's something that you had like, it's exactly like the method that I've seen that I've shown you before. Through the movement of the bridge, everybody goes the same way, and then it starts wobbling more and more, and people are quite happy and smiling about it. They don't realize the danger that they have here. Yeah. And it didn't collapse, but it can collapse. This movement of few meters to the side in this way, it's quite dangerous. And they shut it down and they fixed it, and you don't have this problem anymore. But this is the Millennium Bridge, and you have also another nice thing that I've seen, that dancing in metal concert. When people are doing this photo in the middle, they measure it. It was measured by cameras that were placed above the crowd, and they saw a fluid dynamics in the crowd and measured it. But it's synchronization. And you have also people clapping hands in the end of the concert, that everybody starts clapping and suddenly everybody claps together. You probably heard it more than once. And then you have period doubling with clapping hand. And you have all this research on the synchronization of people, but everything has been done in global coupling. Okay? When you are clapping hands, everybody hears everybody. When you are walking on a bridge, everybody feels the bridge. So it's global coupling. It's global coupling. So everybody is coupled to everybody else. However, maybe this was correct in ancient history, well, when we had to come to a decision on something, everybody went to the city center and talked about it. But the situation today is completely different. And if we look at some kind of, this is for example my Facebook friend network, and I don't know where you are, somewhere here, but it's a complex network. And when you have a complex network, the people that I know are different than the people that you all know, and this makes a very different dynamics. So how human network get to a synchronization? How does such network make decisions? How leaders are formed in such network? When such network is going to break and fail? And this is not only human network in Facebook, but every network that we have in real life also, because I meet different people than you meet. And also what we have in the university or in the city or everything else, then we have, we can have a breakdown of the network, or we can have a sub-network that start believing silly things and stuff like that. Okay? So this is the main motivation of our research, because for the first time we have a system that can actually measure the dynamic of human network even when the network is complex, and we can change the network every we like. Let me start about...
Just a brief question.
Yes.
How do you measure synchronization in this case, or in politics case, or army case? I mean, it's just you define what is an opinion of sorts, and how many people are interacting or agreeing with this opinion. And I see this
measuring synchronization in networks like politics or army or economics is much harder, but when things break down, you see it. And this is why we have our system. Because if we could measure easily how things go in other networks, then we wouldn't need the systems that I will show you. Where you can measure everything, you can measure the dynamics until it breaks down, and then you can measure how the system behaves.
But what is the order parameter that you seek to synchronize?
Well, that depends on different systems has different order parameters.
So here it would be some sort of weird opinions, and the mainstream would ground truth.
Yeah, also, I will talk about fake news and stuff like that, and I will show you.
Okay.
So this is our system. What we have? We have 16 violin players from the Philharmonic. They are all professional violin players, and each one is playing with electric violin. And when they are playing, they don't see each other, they don't hear each other. Each one has a noise cancellation headphones, and all the noise going back to the control. And with the press of a button, we can choose which one is hearing which, or what they are hearing, or maybe everybody hears everybody, or maybe each one is only hearing its nearest neighbors. And we can play with it. And what they need to do is they play the same musical phrase over and over again. And their only instruction is to try to synchronize to what they hear. That's it. So they play this repeatedly, and this is how it looks. And when I just started it, I was very excited, and I bought to the lab 16 electric violins. But apparently, when the violin player comes to the lab, he brings his own violin. So I have 16 violins hanging on the wall. Okay. Okay, and this is how it sounds. And why violin? You can ask about why violin, and violin is because, well, there are many benefits of violin. First of all, violin is a continuous instrument, so it can play continuously. Each note, if needed, can be as long as needed, not like a keyboard when you just press and that's it. And violins are also, I liked it that they move, so you can see with your eyes when they are synchronized and when they are not, because it's almost like dancing when they play. Violins usually have better musical hearing than other instruments, not necessarily, but it says they have. And there are other things that I can talk about violins. And also about how we choose this musical phrase. Also, I can talk about it a bit if I have time. Why we choose this musical phrase. We have also other musical phrases, but they all have the same logic behind them. Why to choose a specific musical phrase. But let's see about some results that we have. Okay. So the first experiment is just straightforward. Let's check how well they can synchronize and compare two situations. One, everybody hears everybody, and the second one is they are all situated on a one-dimensional ring, and each one is only hearing its nearest neighbors. And then we reduce the coupling strength. This is high coupling strength, and it's normalized unit. The coupling strength is the relation between the volume that I'm hearing my own violin compared to the volume that I'm hearing a neighbor's violin. So half means that I'm hearing half of my input sound is my own violin, and half of my input sound is other people's violins. And as I go to zero, I hear more and more my own violin and less my neighbor's violins. Okay? And then you can see that when everybody hears everybody, I have some in-phase order parameter, which means how much they are all synchronized, and it just sticks to one until very low coupling, then it drops to zero. And when I have this one-dimensional ring, then it starts going down and you have like breaks. And, well, I don't need to explain why it happens.
How is it that you can measure the interface all the time?
The computer is doing it. It's not very complicated. I'm just looking at the phase of each one and looking at the average phase of each violin player. Like I can look at the musical phrase, and I can say that the beginning is 0, the end is 2 pi, and that's the phase. And each one, I'm just looking at the average phase, and it's giving me the other parameter. Okay.
And did you change it continuously, this strength? I mean, they start from
Yeah.
each set of dots is a prosecuting in the same experiment.
Yeah, it's the same experiment, but it's a very adiabatic change. It's a long experiment, and I'm changing everything slowly. And I'm looking when it breaks down.
How long did you wait to determine the order parameter? Maybe if you wait many hours, okay, so the same. No, I mean, how do you do this? I mean, you change the strength, and then you wait some time.
What?
And then you wait some time.
Yeah, I'm just changing the strength slow enough compared to the time that it takes them to finish one musical phrase. If I'm doing it slow enough, then every musical phrase is relatively at the same coupling strength.
So what
Yes.
happens, I'm assuming you started from a high coupling and
Yes.
lowered it. Does it look the same if you do the opposite way? You start
Maybe we
from a
didn't do
low
it.
coupling and
Yeah, we didn't do it. It was like a boring experiment. So we did it once, we got these results, and
I'm assuming the
we
players
moved
get
on.
bored.
What?
I'm assuming the players get bored by the end of these curves.
Yeah, but I don't really care about it. Yeah, there are only lasers for me. Okay. But then let's do something. Okay, so this was nice, and then we said, okay, let's do something more interesting. Let's introduce delay. What do we mean about delay? It's the fact that when, let's say that you play the violin and I play the violin, and I'm hearing what you play, and you hear what I play, and then I introduce delay. So instead of me hearing what you play now, I hear what you play like half a second or quarter of a second, and vice versa. You hear what I play half a second. What happens then? Okay, so these are the results. This is only 2 players. I have 1 and 2, and they have coupling, and I introduce delay between them in seconds, and I'm doing it as a function of time. And here you see this color shape. It's this indicates the phase of the player in the musical phrase. So blue means the 0 and the beginning of the musical phrase, and yellow means the end of the musical phrase, which is 2 pi. And you see how we start playing one phrase, the second phrase, the third phrase. And at the beginning, they are synchronized, both play the same. But then we start introducing delay. And when you start introducing delay, something has to break down. And what happens is at first, you can see that they start playing longer and longer musical phrases. And here you can see also the periodicity start to increase at the beginning. And they try to compensate for the fact that you have this delay. This is something that we know of with our big orchestras, and one person at one end hear the other person on the other end in a delay due to the velocity of sound. Just the sound velocity makes it, when you have big orchestra, you have this problem, and they tell them don't play according to what you hear, play according to the contractor, because speed of light wins. But they start playing slower and slower until, well, it can go for a quarter of a second or for half a second. Then something breaks down, and one of them starts to be ahead of the other, and they just ignore the other one, until they reach out of phase. When they reach out of phase, what happens here? One of them is exactly at the beginning, when the other one is in the middle. And it happens when the delay is half of the time that it takes them to play the musical phrase. Okay? Let's say the musical phrase takes us 4 seconds to play. And the delay is 2 seconds. And you are playing this musical phrase in 4 seconds, and I play it in 4 seconds. But we have like this out of phase. So when you are in the beginning, I'm in the middle. But you hear what I played 2 seconds ago, which is exactly when I was in the beginning. So you are satisfied. I hear what you played 2 seconds ago. You are now in the beginning, but 2 seconds ago you were exactly in the middle. So I'm also hearing what I'm playing. So we are both satisfied. Although someone from the outside sees this out of phase, both of us hear in phase. So both of us are satisfied. And this is a highly stable state. When they reach this state, they can stay there even if the delay increases or decreases. All they have to do is change their playing velocity, change the clear distance. And this is what we see. Once they reach this order out of phase, order parameter reach 1, that's it, they get stuck in this highly stable state. They remain there. And if I continue to increase the delay, they just keep on increasing the periodicity. If I then reduce the delay, they will just play faster and faster and faster. They will stay in this state, this out of phase state. This is the stable state. Yes?
And is this related to this verse that they played? Does it happen in other verses as well?
No, it doesn't matter because what they hear is are completely in phase. It doesn't change the phrase. In this case, maybe in this state we can talk about it, but when they reach this out of phase, each player doesn't hear out of phase. Each player hears in phase. Because when you play the beginning, you hear when I play the beginning, although I'm not in the beginning, when I play the beginning, I hear what you played when you were in the beginning. So we both in phase. From my point of view, or from your point of view. From the audience point of view, it's out of phase. And this one works the same for 4 players, 6 players, 8 players. You always see this order parameter reaching to 1. You see this increase in the periodicity. You see this checkerboard pattern appears out of phase. And once they reach it, it's like ultra stable. And it's very hard to get out of this state. Okay. But what happens when we have like odd number of players? So when you have odd number, let's say that both of us reach this out of phase, and then we have Yoav, which is joining us, and he hears both of us. So he needs to choose either join us, me, or join you. So we have this frustration because when we have 3, none of us can be satisfied. And when measuring frustration, I don't need to tell you about it, it's what we like to do in physical systems. It's very interesting when you have frustrated system, then things pop up and interesting stuff happens. When you are considering human interaction, it's even more satisfying because when you get them into frustration, this is how it looks like. And what happened then? So, let's talk about 3. At first, they are synchronized. As we've seen before, you have like the periodicity increase, they start to slow down because of the delay. Then something happened in the middle, let's not talk about it. But then, when they need to reach this out of phase, what do you see?
The 2 are synchronized and
These 2 are actually synchronized to this one. They don't synchronize to each other. What happens in nature when you have frustration? When you are like this bird that is flying in these shapes, and you are flying in the middle, and your bird to the right go this way, and the bird to the left go this way, what are you doing? You go in the middle. So whenever you have frustration in nature, they try to average over your inputs, and they try to reach a solution where nobody is fully frustrated and nobody is fully satisfied, something in the middle. With humans, it's completely different. What you see is just ignoring one of the connection. 1 and 2 just ignore the connections. They just ignore each other. They ignore their ego. And we know that human can do it because whenever you spoke to your friend in train station or in a coffee shop where it was noisy and the noise might be even a higher volume than your friends was talking, you could still understand and talk easily. And this is because of our brain ability to block specific inputs. So this is what they are doing. They are not trying to average over everything and to reach this 0 and 2 pi over 3, 4 pi over 3, which you are expecting with when you are coupled lasers or pendulums or subparticle atoms or galaxies or everything else. But here what they do is they just block a specific connection. So they change the connectivity of the system. They effectively change the network. And we see the same, yes?
Why is the order parameter goes to 1?
Well, this other parameter, you ignore this connection. Okay. Yeah.
How exactly is the delay? I mean, each player hears a delay of, say, a third of 2 pi with each of the neighbors?
In this case, 4 seconds. The delay is 4 seconds.
With respect to each and every player, or there
Yes,
are
yes,
the
yes.
Okay.
Each arrow. Each arrow.
Okay.
If the music sheet is more complicated with the part that is repeats itself.
Again?
When the music sheet is more complicated with the part that repeats itself.
Well, we did some experiments with the more complicated musical phrases and other things happen. Yeah, when the music is more complicated, yes, you know, it's very easy to make things more complicated. We try to find the simplest model.
For example, just let's say one repetition in the middle.
So things, other things. It's like Spaceballs. Take only what you need to survive. So we do the model as simple as we can, and then we start building up. But there are other other directions that we can go and research this, and other phrase or more complicated phrase or other instruments or there are many things that we can do here.
So here we have 4 that can synchronize with 1.
4 and 3 are disconnected. They just ignore each other.
And the others are synchronous with them.
Yes, all of them are out of phase synchronized, and only these 2 just ignore each other. Although they hear each other, they just completely ignore this input.
So the players themselves synchronized.
Yeah, they hear themselves synchronized. You always hear yourself without delay, but you hear other with delay. Okay, and exactly the same things happen when you increase the number and you go to 2-dimensional array. You see the same out-of-phase pattern when you are building a square lattice. And which lattice I'm going to show you now? Triangle, of course. And when you have triangle, then things break down. And they just start to ignore each other, and they reduce the network into actually a square network. This is what they do. They just ignore each other until they build this. Or they can build this one, or they can build this one, or this one. You reach a situation where you have many states which have about the same energy, so it's a glass state. And we don't know to which states they will go. They can go either to this or this or this, and they can also switch between them. And this is a situation that we have observed here.
So some of the grids you show, they have like it's not exactly square, right? And I can see
Yeah, but no, it's like
So
a square.
whenever, so, yeah, so,
Yeah,
so whenever,
it's something that is, yeah.
okay, so it's not like they always ignore one or the
Yeah,
other.
each,
They
they
sometimes
completely
ignore-
ignore. And when you ask them, even in three, you can run the same experiment several times. And each one they will choose a different solution. They can either break this one, break this one, break this one, or reach a vortex. Yes.
This is the two divided system with the periodic boundary condition?
No, here you don't have periodic
So the boundary can play a big role.
Yeah. Boundary will break it. Yes. Boundary will, yeah, right. I didn't think about it. Boundary will enforce them to choose only one solution. Or they will have less solutions, that's for sure. But when you have this triangle, even when there are three, and they choose each time different stuff, sometimes they choose to listen to this guy, or sometimes to this one. When you ask them afterward, did you do something different? Did you feel something? They say, no, it's exactly the same. They are not aware of what they choose. Yes?
The one that is not connected to anyone, did it just give up on something?
We should find. Yes. You know, and when we look at these experiments, it's
But these things are dynamic, right?
yes.
Because they try something, maybe they try something else, and
Completely it happens. Yeah. And this is exactly my second part of the talk. When we study actually how they reach the solution, or not only the solution, but the dynamic to reach the solution. And you can ask, when we repeat each experiment several times, apart from getting, in this case we get different results, but when we look at the other parameter, or when we look at other properties of the system, we actually reach the same results up to the third significant number. This might not be very impressive for you physicists, but when I say it to a crowd in the humanitarian or people that study behavioral science, they just their jaw drops, because it's unheard of, this accuracy. And why do we have this accuracy? We have this accuracy for several reasons. First of all, our system is very quiet. Okay, we actually control which one is dealing with which. We have a complete control of the connectivity. They cannot look, they cannot see. They only hear what we make them hear. And we can repeat the same network with high accuracy. It will be the same network. And we get the same results whenever we change the players, and we did this experiment several times, like 5 times before we publish this result, and with different players.
No,
Se-
when you say reach the same result, what do you mean?
The same order parameter, the fact that the order parameter gets to 0.997. It's getting to 0.997. And the second thing, we are measuring here, we are using violin players, professional violin players. Okay? This is what we do since age 3. Playing the violin to try to synchronize what they hear. That's it. This is all they do in their life. So it's very different than getting some students, paying them 100 shekels, and telling them to do some tasks, which some of them might be good at learning new tasks, and some of them not as good. Here we actually measure human when they do what they know how to do in their native habitat. Okay, so this is the reason why we have such good results, and the fact that we have such a clean system means that we can see, we can observe, and we can study behavior that cannot be observed in other systems, because it just disappears in the noise, and we don't have the noise, so we can measure this very subtle dynamics, very subtle change, so we can see things before things break down. You can see dynamics how a network gets to a state where things will break. Yes.
Right, okay. So maybe you said it not. Does the system, for this example, do you reach a steady state? Or does it always switch or whatever?
It's a glass state. They get to once and then it starts, then they move to another. Yeah, it's something changes.
So you can also maybe introduce some noise in the coupling and then see transition.
I can do that.
The time position of the flower.
Apparently, humans have internal noise in this direction. So, yeah, and I will show you in a second how it affects the other situation. So, if I'll, this was the first half of the talk. So if I summarize what I've shown you so far, so this is the property of our system. We have professional value player, so it's easy control, we have reproducibility, and it's, we saw all this stuff. Okay, yes?
Sorry. One other question. So the coupling is not reciprocal, right? Because it's not. I hear you a second later, and you hear me a second
Yeah.
later. It's
No,
some.
yeah. It's very hard to make you hear me a second
No,
before.
I understand. But then, okay. It's a fun.
Although you probably know me well enough to know what I'm about to say.
Just the price.
This thing this thing already has applications because it means that when a system gets to a stable state, it will remain there. It will just ignore other data. It will just completely ignore it. For example, fake news. When you have a fake news, when you have subsystems that close the loop, subnetworks that makes a closed loop, and this subnetwork believes in the craziest thing, doesn't matter, flat earth. Once you close the loop, it will be completely stable, and it won't have, if you just spread like 99.9% of the network will be good information, you have 0.1% of bad information that will just absorb it. And nothing you will do will change it. You can take this person and put him in space and show him, look, the earth is round, it won't help. Once you close the loop, it's gone. And this actually, we published it before, and you saw it also in the COVID pandemic, when they tried to spread good information, but it didn't help. Once you had like this closed loop, which believes that vaccines are bad, that's it. It doesn't matter.
But you make your leap between your various players with time delay.
Yeah, and they're very flexible leap. Yes, but yeah, we can talk about it. But the fact that you have these subnetworks that are close to each other, and we've seen that once you have like a closed network,
It's more stable than.
yeah, it's completely stable. And they just ignore, when they decide to ignore people, they ignore them, and that's it. It doesn't matter. And we did also other measurement of this. So yeah, and the fact that we have this ability, we can actually see when, if you want to fight fake news in that sense, although again, it's very flexible, I do agree. But I'm flexible, so it's okay. And when you do this leap, when you want to prevent fake news, you need to prevent them before they reach this, before they close the loop. And we are now working on studying how to make networks which prevent it from a topological point of view. Not that you have like these big brothers that says that something spread and just cut it. This is for the Americans. This is how they handle the situation in Ukraine. When you have this Russian site that try to spread fake news, so you just block them. There was someone that block this network, and this is how they prevent this subnetwork to isolated. There may be other more subtle ways to do it. But let's talk about unidirectional coupling. Until now, we had just two-directional coupling. When you hear me, I hear you. What happens when you have unidirectional coupling? First of all, you don't have frustration, right? Because each one only hears one input. You don't have two inputs. There is no reason to have frustration in that sense. Each player only hear one player.
Did not hear themselves?
They hear themselves also, but they hear also one. They need to synchronize to another one. That's it. They don't have two inputs that contradict each other. However, if I introduce now delay, let's say the delay is half a second, and I have here the delay between them. I have 6 players. And let's say that the playing period is 4 seconds. It takes them 4 seconds to finish the musical phrase. You see that something will not work, right? Because if this one hears this one half a second ago, and this one half a second ago, if 3 seconds ago you don't close the loop. So although we don't have a local frustration, we have here a global frustration. We have here a topological frustration. It's frustration that when each node in the network doesn't feel it, but when you look from outside, suddenly you have frustration. So where is this frustration coming from, and how it will influence? And we are. It's very nice to. I have time to go into it.
We are flexible.
Yeah, more flexible. Good. So, Komamoto model, some of you know it. Then I'm doing Shekel Kolshu, and I'm getting into potential movement in a potential landscape. So I have the delta phi, it's the average delta phase between each player, and it moves according to some potential. And it's nice to have this potential, effective potential, because then it's very easy to imagine what things happen. Okay, it's very hard to imagine how they behave. It's much easier to imagine like a small ball going in effective potential, and then see if it reach like a minimum, and then you know that it phase up, or it just continue to roll down, and then it doesn't reach a minimum ever. So the thing is, we are using this situation. I don't have enough time to get to everything that I want to say, so let's just reach the bottom line. We are using this topological frustrated network to measure a specific thing. When you have a system, sometimes this system can be stuck in a local minimum. And this system it can be that the system is stuck in a local minimum, it can be that the system was in a global minimum, and somehow with adiabatic you moved into a local minimum. It doesn't matter, but the system is right now in a local minimum, and there is a better solution. But to reach this better solution, you need to overcome a potential barrier. Okay? This is well known, this local minimum situation, and we wanted to measure how human network behave. When a human network reach a local minimum, in this case, this value has reached a local minimum, and then there is a better solution. But in order for them to reach this solution, they need a conductor that will tell them, okay, you now stop, you start, and now you started, and then they reach. But there is no conductor. There is no one that knows what is the better solution. They only feel this frustration among themselves, but they don't know how to solve it. And this can happen in many situations when you have a human society that something is changing, and suddenly, instead of being in the state that was until now a global minimum and everybody were happy, suddenly they find themselves in the local minimum and things are not going well, and they don't know how to find the local minimum. And this was measured with ants for example, how when they need to find some kind of pass to get the food into the net, and sometimes they get stuck in a local minimum, and how they find the global one. So there are different methods how to overcome this global minimum. You see it also in other animals. And this is the main thing that we wanted to measure here. So the global minimum in our case is how they play, which phase difference, average phase difference they have between them. And when you have zero delay, then obviously the minimum is just a zero phase difference. Everybody plays in phase, everybody plays together. There is no delay between them. But when we increase the delay, and this is this situation, okay, this is this graph is just cross section of this point. This is zero. Okay, so we have here the minimum, here you have this potential, here you have the local minimum. But when you start to increase the delay, suddenly this in phase is getting higher and higher, and this vortex state, when you have like this phase difference between them, where there is a phase difference between each adjacent players, it becomes deeper and deeper until this one is the global minimum. So the global minimum in this case, and I can show you how it looks like. Okay, I can't. Okay, yes, I can. Okay, so suddenly this becomes the global minimum. Obviously, this.
Sorry, I'm curious, but what's the idea behind how do you determine the effective potential? So the effective potential appeared in the equation slide ago.
The effective
How do you decide what is it? Do you do it according to the measurement? You somehow refer to
This effective potential, I have analytical solution for it. When I have the coordinate model between them, I can measure the average phase between them, and this average phase I can measure the dynamic between them, and I have the differential equation.
it's a property of the parallel model.
Yes, yes. It gives me the potential of the system. Yes. So when I'm shifting adiabatically the system from 0 delay to t over 4 delay, in this case it's 4, I'd say players, so it's t over 4, then I get this, it's supposed to be 4 players. Okay. Then I get that the vortex is the stable state from now on. So they prefer to be in a specific phase, but they are stuck here. So how they can reach here? And not only that they are stuck here, each player has only one input. So they don't have two inputs to choose between them. They only have one input, so it tries to follow this input, and that's it. So how the system goes from this to this? So we found several techniques that they are using. First of all, and I'll be fast because I'm almost out of time.
So you can take like 10 minutes.
Okay. Okay. So first of all, we've seen that they are slowing down more and more and more. This slowing down of the phase that we've seen before was very obvious here. You see this is the phase and this is the frequency. The frequency is the black. And you see that the frequency or tempo is just going rapidly low, and we see it only in numerical simulation. And when you look at the effective potential in that case, well, what they do, here we are changing the coupling delay, we are getting the coupling delay larger and larger as time goes by, but since they are slowing down, this just stays the global minimum, because they are playing just very slow compared to the delay. So the delay is negligible. So this is the first technique, which we have seen before sometimes.
It's strange. What causes a violent player that hears only one violent player
to slow down? That's a very good question. It's well, okay. So if you look at it, the joint's just going down like this. We are going in some kind of oscillation. So these oscillations are related to the times that the information goes around. Okay, so they're going up faster, and so they are just overshooting and undershooting all the time. They're just doing this. They can slow down so much until you reach an oscillation depth. What is oscillation depth? It's something that we know that happens in non-linear oscillators, coupled non-linear oscillators. Sometimes the oscillator just died. The oscillation dies, and we see it. If you see the phase as a function of time, so again, this is the phase, 2 pi means that they finished one musical phrase, this is the second musical phrase, and this one goes so, until they play just the same note. They just play the same note for over 40 seconds. 40 seconds, and that's it. 40 seconds they play the same note. When you are playing the same note, that's a stable solution, because then you are synchronized no matter of the delay. You always hear the same note from the others. So they just reach an oscillation depth. And we know about oscillation depth, and we know that there can be oscillation revive. You can revive the oscillation if you put external perturbation. However, as I told you, humans has internal noise, and they suddenly someone start playing again. With no reason. Someone's just after 40 seconds of playing the same note, we decide maybe this is and once this player start playing, the other follow, and you immediately reach this voltage state. And they reach this, so the topological chart reach one, so they reach this voltage state. Another thing that we see sometimes is amplitude death. This can happen when one of the players just stopped playing. Okay, so he has this, and it's very interesting because, again, what you have said, they only need to follow one, and still they are in a frustrated state. Why this frustration came from? Where this frustration came from? But when one is too frustrated, stop playing completely, you see the amplitude drops down, and then just wait, and once one of them stop playing, then immediately it breaks the chain. If it breaks the chain, there is no problem finding the vortex solution. Once they found the vortex solution, they continue playing, and you have this vortex solution, and everything will go. And then when you increase the delay more, and you need to jump to the second vortex, second order vortex, again, the same person, just stop playing. He will not join us in the next stage. And the last one, which again is somehow related, is the same ability of humans to actually decide to which input to listen. And in this case, what we see here, again, this is the phase of, in this case, 8 players. So we have the first state when everybody is in phase, they just play together, and then one of them decide stop listening to the other, and this is the blue one, and everybody follows it until they reach this vortex state. This is the first one, the vortex state, and we see how this one stopped following, and we can measure. So what this player is doing is just ignoring the input. Once this player ignores the input, if we look at the effective potential, it just dropped the potential barrier between them. So now the system can go smoothly from the in phase to the vortex state. And the same things happen when you continue to increase the time. In this case, 16 players, we have seen the first, this 0 state, that is the first topological chart, or the first vortex order. The first vortex order, or the second vortex order, I mean how many times you finish 2 pi when you complete a circle. So the first vortex order is 2 pi, the second vortex order is 4 pi, and 6 pi, and so on. And we can see it also in the how they move smoothly in the effective potential landscape. How they move from 0 to first order, second order, third order, and so on. So we have still many things to measure, and we have done some experiment now. This experiment was done in the Technion. This is in Schneiderman's lab. And then we have this very big screen where we analyze the phase of each player in real time. We can see things as they happen. But we still want to measure dynamic networks because all these networks were still stationary. We set the network and we let it roll over. We didn't shape the network as during the experiment, and we want to do it smartly, not just telling the network, okay, now 10 seconds we do with this network, and 10 seconds with this network, but we want systems that will analyze, for example, which connection is being used and which connection is being ignored, and changing the amplitude or the coupling strength of this connection proportionally to how it's being used. So it will be something that it can be similar to a neural network where connections that are being used are stronger, or we can do the opposite. So connections that are being used will be weaker. And this is, by the way, is related to what I told you about a network that topologically will prevent sub-network to happen. So it will topologically prevent fake news for spreading. It's something that is dynamic, something like this. Unequal network where not all the connections have the same delay or have the same coupling strength. We want to measure decision making between them and use them, how they choose which leader to hear, if you have two. Until now, all the players were, well, it was a democratic situation where all the players were equal, but we can make leaders, we can choose ones that will not hear anybody, but everybody will hear this one, or two of them. And then the network will need to choose who to follow. So we're doing this, and this is also leaders and followers. We can look at the network and measure from Sean theory how the information is flowing in the network and how they choose where to flow the information, or who is more leaders than others. And we want to measure also human versus other. So this is the thing that we are doing. And maybe 1 minute I'll take from the time, and because Elad took it to a different level, because Elad is a musician, Elad Schneiderman is also a musician, and there are mainly two types of music in the world. You have either this orchestra or player that you are following a chore, and you are just following the conductor, and you are doing or you have this improvisation, jazz style, where everybody is improvising, but everybody hears everybody, so you're improvising into what you hear. And what Elad did, he took our research and invented a new type of music where he lets the violin player play, and during their play, behind the curtain, he's changing the coupling, he's changing the network, he's changing the delay. And this is how the musical piece is being created. So each player doesn't hear the musical piece, only the audience hears it. The players are just frustrated and trying to follow what we are doing to them, but the audience hears something completely different. They hear the complete piece that we have, and this one you can hear it in Bar-Ilan University. We have this dome where this is when you can hear his musical piece, and this is something that he invented thanks to this research, and that's pretty much it. So this was a collaboration with Neil Davidson, obviously, and this one when Elad was still a student in Stony Brook, now he's in the Technion, so I had to change it, and that's it, pretty much.
Are there any questions?
Other musicians also emotionally frustrated, or they enjoy the
Well, I think it depends which player. Some of them told me that it it's like a meditation for them. And they enjoy very much being in this experiment, and they come back to our experiments every time that we invite them. Then they come, and some are just too frustrated and doesn't go back. And we have also other results which we try to analyze, and we are still stuck in many of them. So I'm very open to ideas about how to address these things or new stuff that we can study in this. But this system is unique in its way to measure the dynamic of human network, which cannot be done in any other experiment.
You need to be careful to not create a bias based on what musicians decide to come back for the.
Well, yeah, but you know, since we are, they have a very tight schedule, so usually we don't have the same musicians. Anyway, maybe one or two come back, but yes.
Is it defined as someone that only directs, is not directed?
Yes, a leader, well, not always, because you can have a leader that everybody follows, and you can have a leader that follows everybody, and he's still the leader, because when you look at how the information flows, you see that the information is flowing from him to the rest, even though that he is behind. So there are leaders that are behind, and there are leaders that are ahead, and they are still the leaders. Yes.
You said something about the interactions, and I'm a bit confused how to think of them being reciprocal or non-reciprocal.
Also, this was the first time that I was thinking about reciprocal, so it's very hard for me to answer. What is reciprocal in that sense?
If I could, I guess it depends on the model that you want to project your interactions on, but if I can have my interactions as some symmetric matrix between the different elements, or if I could break the symmetry of this matrix.
It's not symmetric. Symmetric will be the same time that they one to two or which is
That's what they have.
I think it's symmetric, but it's not hermetic.
Okay. Let's say, what do you get? And as it gets to the bus center, you get a souvenir.
Thank you very much.
Pizzas are outside.